Here's the big picture of ezRA and all how its data flows around. We started with collecting data with a physical antenna in hardware. It had a coax into a radio. The radio was controlled by some software. Many are available. ezCall is one of them. It created some kind of data file eventually. This is the .text data file. I used ezFix to change some of the data files for examples back in the interference filter video. In the beginning, we looked at those .text files with Excel and produced some graphs. We later ran ezCon, and we saw many plot files. ezCon, every time it runs, it creates a .ezb data file, which should be smaller than the first one over here. And it has a lot of math computations stored inside it. At one point, we looked at histograms and sorted data files. That was with ezplot, and we saw those plot files. And now we finally get to ezSky. That's the fun part, seems to me. We take ezb files and convert them into plot files, maps of the sky, the radio sky. We first talk about Radek sky maps. Radek, right ascension, declination. Those are simply the names of the coordinates used on the two axes. Buzz Aldrin was the second fellow to walk on the moon. He signed this saying that this sheet of paper from one of his notebooks made it to the surface of the moon on Apollo 11. It is a star chart, just in case they had to do some navigation. It includes Cygnus the swan. Here is Scorpius the scorpion. And over here is Cassiopeia the queen. This is page 2. On page 1, it gets a little more complicated and has more coordinate stuff. Again, here's Cygnus the swan. Down here is Scorpius the scorpion. And over here is Cassiopeia the queen. We talked about coordinates. Way up in the top, maybe you can't see it, says 0 and counts all the way across the top to the left, increasing all the way up to 24 hours. That is right ascension. It's a very old name for locating things on the sky. On the y-axis, there's a 0 in the middle, and it climbs up to plus 90 at the top, and it goes down to minus 90 at the bottom. With those coordinates, we can locate any spot on the optical star sky and find the star that lives there. Now we have a location for all the optical stars in the sky that we can see with telescopes and have their positions measured in right ascension going across from right to left and declination going up and down. As the Earth travels around the sun once a year, the stars behind the sun change. It's as if the sun is moving across the sky of stars. That's reflected by this curvy line, sinusoidal curve. It starts with the first day of spring. The sun appears to be in this spot on the sky. 3 months later, the sun has traveled across the sky up to this high point. The sun is high in the sky, and for the northern hemisphere, we call that summer. The sun is beating down. 3 months later is the fall equinox, when the sun appears to be directly above the Earth's equator. And 3 months later after that, the sun is low in the sky for the northern hemisphere. We don't receive much sun, and it's cold. It's wintertime. In the southern hemisphere, it's the reverse. The sun is now high in the sky, and they call it summertime. 3 months later, the sun has traveled over to the beginning spot, the first day of spring, and we begin a new year. Another curve that's harder to see is, as you follow my cursor from the top right, seems to come down here through a whole bunch of activity, and then curves back up here through Cygnus and out again to the left. That turns out to be the plane of the Milky Way. Both of those curves are sinusoidal across the sky. This is because the north-south axis of the Earth's rotation does not align with the north-south axis of the sun's rotation, nor even the north-south axis of the galaxy's rotation. Said in a different way, the Earth's equator is tilted 23 degrees from the Earth's path around the sun. The Earth and the sun travel around the galaxy, but they are in the plane of the galaxy. And the Earth's equator is tilted 63 degrees from the plane of the galaxy. For those folks in Denver, Colorado, at about 40 degrees north latitude, they see these stars directly above their head at 40 degrees declination every day. Now, the bright sun might block their view of them, but those are the stars that pass over their head from right to left every day. For folks in Kenya, in Africa, at 0 degrees, right on the equator, they see these stars pass directly overhead every day. And for those folks in Sydney, Australia, at Earth latitude about minus 33, they see these stars pass directly over their heads once every day. This is what it looks like for the stars with light, optical viewing with telescopes. But for radio telescopes, they see the sky also. Same coordinates, different picture. We have the coordinates across the bottom, 0 through 24. That's right ascension, measured in hours. The 0 is in the middle, declination up to plus 90 and down to minus 90. The same points in the sky. The radio sky looks different than the optical sky. We don't see the stars particularly, but we do see a great big curve of activity shaped like a great big U that's going across the sky in the same location as what I said earlier was the galaxy, the plane of the galaxy. We also have the curve of the ecliptic going across here. The sun follows this curve along with the planets, I suppose, but the sun is emitting a lot of radio energy, and that may affect your measurements. There's some exciting spots on the map marked in red, which have a bunch of radio emission coming from them, particularly down here near Sagittarius A star, where the center of the galaxy is. They now think there's a black hole at the center of our Milky Way at this location. You'll see that on the left-hand side, over here near the center of the galaxy, we see a lot of activity. And when we're kind of far away from that location, the galaxy doesn't, the galactic plane even, doesn't look very bright. The action is over here near the center of the galaxy. That's where most of the galactic hydrogen is for us. Good, so let's go run some data. We have this data file we're quite familiar with in other videos. In 2023, in February 9th, starting in the 0 hour of Coordinated Universal Time, the data was collected. EZCon created a .ezb file. in the same directory as all the plots are, right at your feet, wherever you ran the program. And we simply call upon it. py in Windows for Python. We want to go up one directory, down one directory into ezRA, and find the Sky program. It's a Python program, so it ends in .py, and we spell out the name of the ezB file. Because so much calculation was done with ezCon, these ezB files run very quickly with ezSky. We get 13 plots in only 9 seconds. The first couple of plots of ezSky are the data it just read in to make sure it understands what you provided. If there's some misunderstanding, let's catch it as soon as we can. This is the same plot that you've seen before. For each sample in the data file, ezCon recorded the average value of that sample spectrum and recorded that one single number in a column in a .ezB file. Here it is, ant B average all the way across. It starts out kind of low, has a bump, goes back to low, has an even bigger bump, and then finally finishes off. ezCon, for every sample, calculated the right ascension. It took where the telescope is on the Earth, what time it is, and where the telescope was pointing, the azimuth and elevation, did a bunch of math, and came up with a number for right ascension for that one sample. That's true for all 908 samples. In this example, it starts out pretty close to 24, climbs up to 24. At 24, it wraps around back down to 0 and climbs steadily in time all the way up to almost 24, which is just about the same value as when it started. It also recorded the declination. Now, that's not very fancy because there's a simple calculation between elevation of the telescope and declination. I have to think about this each time. I take my latitude on Earth, and I know the declination of the stars directly above me are that same number. For the declination of the stars at the horizon, I move my eyes from straight overhead down 90 degrees to the horizon, and that's the declination in parentheses for the horizon from my location. And with that information, now I can add the elevation of the telescope, which is the height above that horizon, and we have the declination for where the telescope is pointing. I did a drift scan where I set the elevation and never changed it. Which gives me a declination of about 7 degrees for every sample all the way across. A dull graph, but useful numbers. We know the right ascension, we know the declination, and now we have a value to plot on here. There's a thin black line which represents the average of the signal shown, in this case, ant B. And the green dots are simply the vertical offset from that average value. We see 2 bumps. We see a big bump on the left, and we see a lesser bump over here on the right. This data file actually started way over here someplace, climbed up to 24, we saw that on the graph before, zips around to 0, and starts climbing across the sky from right to left. That's the increasing right ascension. We see a bump of data, it goes along, and then we see a bigger bump of data, and then the data file ended. The drift scan trace advances to the left. Why? Well, in the northern hemisphere, if you stand in a field looking south, the Earth rotates, and the stars, like the sun, rise in the east and travel to your right across the sky and set in the west. This star map presents that view. It is as if the whole star map, with all its stars, slides slowly to the right. With the star map moving right and your telescope locked in position, it is as if your telescope is drawing a line advancing to the left. We see we're going from looking above the galactic plane up near the north galactic pole, over here with a drift scan into the below the galactic plane, down in here. When the drift scan travels from positive galactic latitude to negative galactic latitude, positive to negative, we travel over an exciting part of the galactic plane where there's lots of hydrogen over here near the galactic center. Compare that to traveling from negative galactic latitude to positive. We travel over another part of the galactic plane, but there just isn't much hydrogen out here to see. So this drift scan crosses the galactic plane in two places. How close did we get? Where is this maximum peak value compared to the galactic plane? Let the computer do the work. There's a computer program to put a green dot at the right ascension and declination of that maximum value. Same is true over here on the right side. And it turns out the green dots are pretty close to the center of the galactic plane, where the galactic latitude is defined as being 0. Now, it could be that the true maximum signal is not on the galactic plane, but it should be close. And so we put green dots and see how close we got. Instead of using that vertical offset graph, how about changing colors? Brighter colors like yellow for higher values. We've seen that before. We see a bright yellow when we cross the galactic plane on the left, and kind of a brighter red over here, at least to the values defined by the color bar down here below. Well, that's nice, but I want more data. Let's go out there and collect more drift scans. Point the telescope at a different elevation and let it run. Let the computer collect more data. And we get more lines going across. They're always horizontal lines with drift scans. Same declination all the time. The intensity changes as we change, and we can plot that in the same way as before. We start to see little bumps in the right places. This is encouraging. And we get to see the little green dots pretty well align with the galactic plane. We can plot the same information with color. Along the galactic plane, we see a little brightening of each one of these purple lines. That's encouraging. So between these two yellow spots, there's a bunch of data in the middle that's missing. Well, we got the computer. Let it predict what those values should be. If we have a bright spot here and a bright spot there, what should be the color of the spot in the middle? And that's true for all the other dots on the screen. Let the computer predict, let it forecast, let it interpolate the data provided, and fill in the rest of the dots. Well, it's starting to fill up the whole screen. We got dots everywhere. The shape of the data starts to look like a U going across the screen. But the data is only valid for where we have those little thin cross lines where we actually collected data. There's parts where we did not collect data. Up here near the North Pole, near Polaris, I need to collect more data. And down near here, near the bottom, the Earth got in the way for my telescope on this part of the Earth. I cannot see these declinations from my location. Just as we were using right ascension and declination to map the sky already, we can use galactic coordinates to map the galactic sky. Let's define what those are. Let's look at this image over here on the right first. The Milky Way is a large disk of stars, much like a galactic round pizza. In the center of that pizza is a black hole, and about 2/3 of the way out is our sun. If we look along the plane of the disk, that would be 0 degrees galactic latitude. Looking above the disk, all the way up to 90, is positive galactic latitude. And looking below the disk, all the way to -90, is negative galactic latitude. If we look down on the great big pizza, we can see the black hole here at the center, and our sun spaced away from it. Hurrah. When we look towards the galactic center, that's defined as galactic longitude 0. If we look to the left of that galactic center, that's a positive degree. 90 degrees is directly to the left, and 180 degrees is behind us from the galactic center. To the right is negative degrees, all the way around to -180. For every sample in the data file, ezCon calculated what the galactic latitude should be in degrees. The galactic plane is right down the center at 0. Sometimes we're looking north of that, and sometimes we're looking south of the galactic plane. This one's more complex. This is galactic longitude, looking left and right along the galactic plane, and it's complex. The curves are remarkable. They're all combinations of trigonometric functions, but there could be 3 or more functions involved. Oh my. Hooray for computers. With those 2 coordinates, well, let's go plot the data. Our drift scans are these thin black lines circling along, and every so often they cross the galactic plane where the galactic latitude is 0. The center of the galaxy would be at 0 longitude and galactic latitude of being 0. So here's the plane of the galaxy starting to be lit up. Sometimes our drift scan is north of the galactic plane, and sometimes it's south. When it is crossing from north to south, from positive to negative latitude, we see that we're in a brighter section of the galaxy, near the center of the galaxy, here at 0, 0. This graph actually represents a sphere looking out. And so all these points along 90 are actually 1 point. As if there was a belt in that top section, let's pull them all together into one spot and gently adjust all the other dimensions. And we get something that looks more like a sphere from the inside, as if we're inside a balloon looking out, looking to the left, looking to the right, looking all the way behind us. This is what the data looks like. We see bright galactic hydrogen down the plane of the galaxy horizontally. There are parts of the galaxy we can't see. Down here, the Earth is in the way. And over here, I haven't collected enough data up near Polaris. The data is only valid where these drift scan traces show. And so the computer is simply making up results where it does not have data. Beware. Well, that's good, but we want more data, more drift scans. At the Little Thompson Observatory in Berthoud, Colorado, we have a 16-foot dish that's been collecting data for a while. We see bumps where there should be bumps. That's encouraging. But my gosh, there's so many of them. Maybe there's a better way. Let's view the same data, but by color. And this looks a little less confusing. We see a bright spot where there should be a bright spot as the galactic plane curves around on the screen. But over here on the left, particularly, I see a jagged pattern. Let's let the computer interpret between all the true data points. And that makes the screen a little bit smoother. So this is a plot of many drift scans, including drift scans piled on top of each other. We're averaging drift scans now, just to make the data even better. This is a different kind of plot. It doesn't show any intensity from signals from the sky. It is the count of how many data points are on each little pixel dot on the screen. So the screen is represented by little boxes, 1/2 degree in declination by 1/2 degree in right ascension. And this plot keeps track of how many data samples are in each box. So many data files that we end up with a purple color. Purple is about 100 data samples per box. As always, we want more data samples per box. In galactic plane, it looks like this. We're getting more drift scans, more of those curvy little black lines curving around and filling up the data space. Hurrah. Where we have no data, the computer is making it up and doing the best it can, but I don't believe it. I need more data up here near Polaris, and I need data where the Earth is in the way. We see a bright line where it should be along the galactic plane. If we take this same graph and try to make it more spherical, here's the plot for that. It looks about the same. We see a galactic plane across the horizontal center of the graph. But it's not really true. How come all this bright stuff in yellow is here? Is it really that way? Let's look at the data. If we plot all the data in all the time, we got 1.6 million samples all collected along here, and we see a bump in the middle. That's what the bright spot is on the previous graph. Turns out that data was collected in the wintertime, when all the amplifiers and electronics were nice and cold and had high gain, giving us a loud signal. I need more reference signals. This was all done with ANT-B. That was the best that I had at this point. Reference signals would help. The next thing to do is not even change the hardware, but just change the software from the Haystack program to ezCall, which knows how to change the frequency being received and could look at non-hydrogen frequencies, like 3 megahertz higher where we don't expect hydrogen, and compare that to hydrogen. That might prove to be an easy reference, even without changing the hardware, by putting a resistor near the front of the first low noise amplifier. And again, with using the .ezB files, that allows ezSky to run quickly. This example of 363 ezB files, all collected in LTO16H directory, with 1.6 million samples, it creates 15 plots in only 36 seconds. Here's the simple command I used. Python, ezSky like before, and simply referring to a whole directory of ezB files to go study. By default, ezSky simply uses column 14 of the ezB file. That's ANT-B signal. But you can choose any other column, like 16, which is ANT-RB, or 18, which is ANT-XTVT. Here are the commands to do that. Again, Python, ezSky, some data file, and use the argument ezSky input and provide a number on the end. To allow comparison, that column number is in the plot file names. Here we see 14 and ANT-B average written out. These are the same plots, but now with 18 ant XTVT. ezRA continues to be updated. You've already seen this sinusoidal projection of the radio sky. ezSky now offers a mulvide projection of the radio sky. This projection is popular in professional papers. Down here in the bottom right, there are parts of the radio sky that LTO-16 cannot see. The Earth is in the way. LTO-16 also didn't collect any data up here near Polaris. First, that masking on the right for what the Earth blocks. The LTO-16 dish is at Earth latitude 40.3 degrees. That means the stars directly above are at declination 40.3 degrees. The declination of the LTO's horizon is 40.3 minus 90 degrees, meaning minus 49.7. So I want to mask for minus 49.7 down to minus 90 degrees declination. We run Python and ezSky and all the necessary data files. We ask for an ezSky mask out. It's a list of 3 items. The last 2 are the values of declination, minus 49.7 all the way down to minus 90. And I use those 2 values as part of the file name. It takes a while, but in 12 minutes, ezSky creates a fairly small data file. Because it is a compressed file, Python puts period NPZ on the end of the file name. To use that mask, we run Python in the normal way with ezSky and all the data files. This time the command line keyword is ezSky mask in, and then the long file name. That part of the sky is blocked out in white. Here's the sinusoidal projection. And here is the mulvide projection. And now for the second mask. The LTO-16 dish did not collect data for the whole sky. When we ran ezSky, one of the things to flash across that screen was a little bit of section about ezSky 020 plot. And part of it talks about what the maximum declination was that was plotted. We can use that number, 43.5, and I add a 3-degree spacer to come up with 46.5. So I want to mask from the North Pole at plus 90 degrees all the way down to 46.5 degrees declination. Like before, we run ezSky, we collect all the data files, we need ezSky mask out. It's a list of 3 items from 90 degrees, that's a positive number, down to 46.5. I give a file name using those numbers. And in 12 minutes, I get a new binary data file, a mask file. To use the mask, we run ezSky and ezSky mask in and the file name. And in fact, if you want to use both masks, just do that twice. ezSky mask in with one of the mask names and ezSky mask in with the other mask name. Both masks in place. But maybe you want one mask file name. There are ways to combine masks. We run ezSky just like before with the ezSky mask in and the first mask file name. And then we add to it ezSky mask out with 3 items. What else do you want to add? From 90 down to 46.5. And what do we call it? That's going to be very long the old way. How about ezSky, LTO, and not masking from 46.5 to minus 49.7? Not masking. In 12 minutes, like before, it creates the file name. And now you use it the common way. Run ezSky, ezSky mask in, and the new single mask file name. It looks just like before, but with one file. But I don't like that white in the middle. I want to start coloring it in different ways. In Windows, the Paint program has a small paint can to pour color into an area. I poured green in one area, and I poured yellow in the area. It fills out all the way till it finds another color than what you poured into. This is related to the next program, ezGal. ezGal concerns itself with data near the galactic plane. But ezSky provides one sky projection that's helpful. The LTO-16 data set includes data all the way from the North Galactic Pole to the South Galactic Pole. See how the drift scans come up, come down, and then come up again during the course of one day. If we take all those galactic latitude values and sort them by their increasing value, we get a slow curve of lots of values. ezGal focuses on those values near the galactic center at 0. Here is shown the galactic latitude samples between plus 30 and minus 30 degrees. It was created with an ezSky keyword of ezSky, gal crossing, galactic latitude, and the value 30. With that value of 30 shown in the top left, this is one of the ezSky plots showing those drift scan samples that meet that criteria. Thanks for coming. Have fun with ezSky and share your successes. See you in the next video.